and Ocean Acidification Network State of the Science webinar series. The title of today's presentation is Modeling Coastal Acidification and Linkages with Land-Based Nutrient Loads. This series is hosted by the Southeast Ocean and Coastal Acidification Network, or SOCAN. In short, these series lay a foundation for the state of the science ocean acidification science in this region. These webinars are intended to create a dialogue among scientists to identify what we know, what we don't know, and what research in other regions of the country can be applied to our region to help us better understand ocean acidification and its impacts as we move forward. Webinar participants will be able to collaborate better to understand and adapt ocean. I'm Paula Keener with NOAA's Office of Ocean Exploration and Research, and I'm a member of the SOCAN Steering Committee. And I'll be moderating today's session on behalf of the committee. Jen Bennett-Mintz is Education and Outreach Coordinator for NOAA's Ocean Acidification Program, and Jen is on the line with us, and she will be helping to facilitate today's session. During the presentation, all audience members will be in listen-only mode. You are welcome to type questions related to technical issues or for our presenter into the questions box in the right bottom of your control panel on the right-hand side of your screen, and we will be monitoring these questions during the presentation and will either respond to them or pose them to our presenter. We are also recording this session, and the video recording and the PDF of the presentation will be available on the SOCAN website. We are very excited today to have Dr. John Lehrter, our speaker, and John is a research ecologist at the Gulf Ecology Division within the U.S. EPA, Office of Research and Development. John is the lead of an interagency, interdisciplinary team of scientists investigating ecosystem response and recovery to changing nutrient loads. This work includes field and laboratory studies of nutrient dynamics and effects, model development and application, and ocean color remote sensing studies. John's current work is the linkage of land-based nutrient loads to coastal hypoxia, acidification, and other eutrophication impairments to aid decision makers in the management and restoration of coastal ecosystems. John, thanks for joining us. I'm going to turn the presentation over to you now.
Okay, thank you, Paula. If I could just get a quick confirmation that you're seeing my screen.
We can see it. Thank you.
Great, great. Well, thank you all for joining us this morning, and it's been a really enlightening seminar series. I've been able to catch most of them since they started late summer, and I think it's a good time to have a modeling presentation. It's sort of the way I look at modeling is it's a synthesis effort to bring together all the ideas about this topic, and it's certainly something that's needed to guide policy and management decisions. And so I'm going to be talking about both coastal acidification and hypoxia, and the reason that I want to focus on hypoxia as well is that the CO2 system processes that are part of the coastal acidification problem are really just the other side of the equation of the oxygen equations in dynamics from primary production and respiration. And so we've been focusing on acidification in this seminar series, but within EPA and elsewhere, people are recognizing this concern about the co-occurrence of acidification and hypoxia. And first I'd like to just start by acknowledging that this is a very large collaborative effort. There's a couple of EPA offices that are very engaged in this. We've had really great support from EPA's Office of Environmental Information, which houses the EPA Supercomputing Center. Many of the modeling results I'll be showing you today are run on a supercomputer, and so we do require expertise to help with that. We've had long-time collaboration with the Naval Research Lab at Stennis, Mississippi, and then terrific collaborations with some academics, in particular at Dalhousie University, LSU, Texas A&M, and University of Delaware. So I'm going to begin today by sort of setting up the problem and explaining our current scientific understanding of how acidification and hypoxia are both linked to land-based nutrients. I'll tell you a little bit about the model development process and where we are with the modeling. In terms of actual case study application, we're been working in the northern Gulf of Mexico now for about a decade, mainly on the hypoxia issue, but over the last 7 or 8 years, coastal acidification is high on our radar, and this is a good system for modeling because there have been some publications that have shown the relationship with coastal acidification and hypoxia in this area. And then finally, I'll finish with some model scenarios that we're thinking about and actually doing in relation to nutrient load reductions and also the influence of climate change on acidification and hypoxia. So this is the only slide I have about aquatic life impacts. I think we've heard a little bit about this in some of the previous seminars. We know that lower pH and changes to the CO2 system are a threat to marine flora, particular shellfish and coral reefs. And we're learning a little bit more now with some recent work showing synergistic relations between low pH, low oxygen, increasing sea surface temperature, and other stressors. But we don't really have still a very good handle on these synergies. We do know that these combinations of, for example, low pH and oxygen do seem to have a greater impact than either stressor alone, and there's been a few good works on this recently. But we're still, most of this research is still sort of mesocosm and aquaria type exposure and done in the lab, and so it's still difficult to scale these efforts to what's really going on in the ecosystem, and especially I think in this multiple stressor type world where we're beginning to appreciate this, we do need more field studies and more realistic exposure and response systems so that we can take these results and scale them back to an estuary or to a coastal system. Okay, so I'm going to begin with, what do we have in terms of our, ability to mitigate, respond, and potentially restore systems that are influenced by nutrients, and in the case of, in particular, for coastal acidification. This Kelly et al. Paper a few years ago was really the first effort to lay out what the policy options are and what the land-based contributions are to coastal acidification. So I'm going to walk through this quickly, but we have, it's really a multimedia problem. We have air issues, we have NOx, SOx, CO2, and other emissions that contribute not only to greenhouse gas and global warming, but also to acid rain and nutrient deposition. And of course, we have runoff from stormwater, from impervious surfaces, as well as point source inputs, fertilizer inputs, erosion, all of these different types of activities that result in nutrient loads. And we really kind of have a patchwork of policy and management to deal with these issues. And so, for example, with the Clean Water Act, we have the ability to manage stormwater and point source inputs, as well as manage the conditions of riverine and coastal ocean ecosystems. The Clean Air Act is a great piece of legislation that's allowed us to reduce the air pollutants that contribute to this problem. Now, when we get into the actual coastal zone, though, for issues like erosion and non-point source nutrients, the legislation available for handling this is more difficult. We do have legislation like the Coastal Zone Management Act that does allow for conservation and protection of critical areas adjacent to estuaries and in the coastal zone. And then largely we have a lot of state and local policies for dealing with some of these non-point source issues. So the point is that we have a lot of different management and policy options, but none that are really targeted at addressing coastal acidification and, for that matter, coastal hypoxia that's outside of state waters. And so what we're looking for within EPA and also in other management organizations is we would like to know for any of these types of reductions, if we do something in the air, the land, or the water, what is the ultimate change in the load that's delivered to the estuary, and then how does that manifest improvements in water quality? And so I just wanted to show this because this is kind of our, I guess our main objective overall is a development of a multimedia nutrient modeling construct, and there's really a lot here. I don't expect everybody to absorb this, and if anybody's more interested, there's a recent report describing our nitrogen and co-pollutants research roadmap, and this figure is from that document. But we're looking to put together, for example, land models with air models, with hydrology and water models, and coastal ocean models, so that, again, we can, any change that we can make in those different media, how does that manifest in ultimately what is delivered to the coastal zone? And then how can we quantify that socioeconomically? And so, for example, for air quality, there's been this tool called BenMap developed, which is a socioeconomic toolbox to evaluate how changes in air quality result in improvements in people's health or smog, other issues like that. But we really don't have that for water quality, and that's something going forward that, at least in EPA, that we're really keen on developing. And so today I'm going to be focusing over here on the right side on the hypoxia and pH issue, but this is sort of how it all ties into our nutrient research and management in EPA. So coastal acidification has been described, I think, pretty well conceptually. This is a figure from Wei-Jun Kai's paper in 2011, which sort of really, I think, for the first time laid out the nexus between open ocean acidification and coastal issues. And so if we start with the, I think, more people probably in this group may be more aware of the ocean issue. We're aware that the oceans have been largely where most of the CO2, anthropogenic CO2, has been taken up. CO2 in the water then combines to make a proton, and that proton is what ultimately reduces the pH. And then from the land side, we have river inputs of nutrients as well as CO2 system variables. The nutrients, though, stimulate the production of organic matter, which results in a decrease in CO2 and production of organic matter. That organic matter from the surface layer is then prone to sinking, so it ultimately makes its way down into the bottom water. And then when there's oxygen available, the respiration of that organic matter will proceed aerobically, and when there's no oxygen, it'll proceed anaerobically. In both cases, though, we generate CO2, and that CO2 then also contributes protons, so further adding to the pH impact there. And so let's see, get that off. Okay, and so with that, then we'll step into the model development, and the goal really is to be able to reproduce numerically the figure that we just saw, and with some additional parts to it that are pretty important. So I'm going to start by describing this from the hypoxia point of view, because most of the coastal ecosystem models have been developed, that have been developed for eutrophication have focused on either hypoxia or water clarity or some other eutrophication aspect. So this is a pretty well developed conceptual model. Going back to 30 years in Chesapeake Bay, we've understood this conceptually. Again, we've got rivers that deliver nitrogen, phosphorus, other nutrients. Those nutrients then promote or enhance phytoplankton production of organic matter. That organic matter can then either just sink to the bottom, or it can be consumed by higher trophic levels. So this is a component that we have to include in the model, is the herbivory on the phytoplankton. That organic matter then, when it does get to the bottom waters or to the benthos, it is consumed and we consume oxygen. And then physically, a couple of things that are really key are in coastal waters is stratification. So this picnic line is actually a density gradient that serves to isolate the bottom water from the surface. And so once we get that vertical stratification that occurs, any respiration that occurs below it is consuming oxygen and creating hypoxic waters. And so what makes it relatively easy to take a hypoxia model and to also include the CO2 system is that in many cases, oxygen is being consumed and CO2 is being generated. And so I'll get into this a little bit more, but if we think about it very simply, sort of in the same manner as this conceptual cartoon, we just need to worry about including air-sea exchange of CO2 and oxygen, and clearly these fluxes can go in either direction based on the saturation condition in the surface layer. But then in terms of respiration and production, at the same time that photosynthesis is generating oxygen, it's consuming CO2, and vice versa. At the same time that respiration is consuming oxygen, it's generating CO2. And then as the oxygen is removed, we get anaerobic processes that also generate CO2. So those are the kind of the ingredients that we need in order to have a realistic model for coastal acidification. So we've developed this new modeling system, and actually we haven't even, it's built on several papers that have explained it, but we put it together for the first time in this system that we call CGEM, Coastal General Ecosystem Model. We're working really hard right now on trying to get the first manuscript out that describes the full modeling system. It's a relatively complex model compared to most nutrient models that are currently in use. And so I'm going to just quickly walk through some of the important features of it. So clearly, the first thing we need is a physics backbone. The CGEM model represents the biogeochemistry and kind of lower trophic level ecosystem processes. That has to be married to a physical model, and so we need to have atmospheric forcing. We need to have well-defined boundary conditions. So, for example, we need to know what the river loads are. We need to be able to quantify the ocean mixing at the open ocean boundary. We need to be able to handle things like light attenuation and stratification. And so then we build upon that to include. Here we go. So as state variables, then we include oxygen and DIC and alkalinity as state variables. And with DIC and total alkalinity, we can then calculate the other CO2 system parameters like pH, aragonite saturation, etc. And of course, for the lower trophic level in CGEM, it's important we need to be able to represent how the phytoplankton, they're really the linkage between the nutrients and the acidification and hypoxia. So in CGEM, we have up to 6 phytoplankton functional types. These are 4 of the most common types of phytoplankton that we observe on the Louisiana shelf. So we specify and parameterize how these groups grow and respond to nutrients. How they're consumed by herbivores, macrozooplankton and microzooplankton. Ultimately, how all of this lower trophic level process results in the production and consumption of organic matter. And for shallow coastal ecosystems, it's very important that we have a realistic way to represent the sediments. We know that in these systems, the sediments are often the dominant location of respiration, and so if we don't include the sediments, we're missing a large part of the oxygen and CO2 system dynamics. I'm not going to show very many equations in this talk, but I did want to include just a couple of slides, in particular showing how we're handling the CO2 system and the oxygen. And so these are the differential equations for oxygen, DIC, and alkalinity. The oxygen balance is calculated as the sum of microbial respiration, so this includes both water column and sediment respiration, phytoplankton production, phytoplankton respiration, zooplankton respiration, and air-sea exchange. And you'll notice that DIC, as I mentioned before, is basically the opposite side of the equation for that. And here we define DIC based on Dixon's definition. And then for alkalinity, we also track the alkalinity generated by the microbial respiration, and then we, within we either generate or consume alkalinity based on phytoplankton uptake of nitrate, ammonium, phosphate, and sulfate. And for this biogeochemistry for alkalinity, we follow the equations of Wolf-Gladrow et al. In 2007. And I wanted to point out, for the definition of alkalinity, we include all of the components except for organic alkalinity. And so, for example, Wei-Jun Kai has shown this to be an important component in some of the estuaries that he studied in Georgia. And it's something that we're currently working on incorporating into the model, but we're not there yet with that particular term. And then for sediment diagenesis, as I mentioned, it's really important to include these features in the model. Actually, we've done a lot of work here at the Gulf Ecology Division trying to understand how these diagenetic processes feed back to the water column and in turn influence oxygen and alkalinity and pH. And so just a really quick primer on this, really more to show what we are modeling. We do model all of the major electron accepting processes. So once the oxygen is consumed, the next electron acceptor that's utilized is nitrate, and then we get into manganese and iron reduction, and then finally sulfate reduction and methanogenesis. And for the sediment diagenesis model, we use the code from Eldridge and Morse in 2008, and since then we've collected a lot of data that we use to help us calibrate and understand what the diagenesis model is doing. One important thing I wanted to show here, this is the only other equation slide that I have, and it's really just to point out again that using this reaction scheme from Van Kaplan and Wang, we can account for not only the organic matter and changes variable stoichiometry in that organic matter, but we account for the electron acceptors, for example, in this case, oxygen, here nitrate for denitrification. But we quantify the changes in the CO2 system with these reactions. And so this reaction scheme is something that we had decided on a long time ago because we were interested in tracking DIC, and it turned out to be a fortuitous decision because it's allowed us to readily incorporate the other components of the CO2 system into the model. So then how do we actually take, so the alkalinity and DIC are our state variables, and we need then to be able to calculate the other CO2 system variables, pH, aragonite saturation, PCO2 as examples. And we had started to develop our own codes to do this, and there are many different available codes for this, but there was a paper that was just published this year on the code called MOXIE 2.0, and I think it's probably state of the art. It looks to be like the most up-to-date representation of the CO2 system, and this is the code that's also included in the CMIP models, the climate multi-intercomparison project models. So we just adopted this, and this is a great example of interoperable model code, if you ever hear that term, interoperable. Basically what it means is that we were able to just take their code and adopt it right into our model code with very little effort, and it's all very well documented. There's a publication about the code. But in effect, it computes the carbon dioxide system using many of the variables that we use in our model, atmosphere pressure, depth, latitude, temperature, salinity, alkalinity, DIC, silica, and phosphate, and also computes the air-sea gas exchange. So again, if anybody's more interested in any of this, please get in touch with me. But we think this is a great example of interoperable code, and will certainly helped us to get further along the road in modeling this problem. And finally, when people talk about modeling, I think it means a lot of different things to many different people. And to me, it means really a multi-step process where we begin with observations, we try to understand the observations with the models, and then finally, through many iterations, we arrive at a model that we can use for prediction. Now, this point of view was recently published on in EOS, and I would suggest anybody that's interested to look at this paper. It's pretty nice because it sort of steps through this iterative process. So for example, the Kai et al. 2011 paper, discussed observations of oxygen, low oxygen, hypoxia, and low pH on the Louisiana shelf. Based on these observations, there were some hypotheses generated, resulting in our new CGEM model, how we've taken those hypotheses and put it together in the model. But then there are many other steps that ultimately we would want to go through before we get to a final model that we use for prediction. And so I feel like we're still kind of working in step 2. We've generated our initial hypotheses, but for biological models, this isn't physics, this is biology, and so we don't have exact numerical representations of all of these processes. For some of these processes, for example, like phytoplankton growth dependence on nutrients, there are 5 or 6 different numerical representations that have been proposed. And so we want to do some testing to look at how differences in model equation structure impacts our model skill. So we're doing some of this work in step 2. And then we're also beginning to look at step 3, where we're looking at some model selection, deciding which of the model equations seem to work better than others. And I'll show a little bit of simulation at the end of this talk, really in regards to our climate change simulation. So we're working kind of in these steps 1 through 4, but ultimately for policy and decision analysis, we would want to do these additional steps where we would do a full validation using observations that are different from the data that we're using for calibration and evaluation. And then finally, we would do some predictions. So, we reduce nutrients by X%. What does that get us in terms of hypoxic area or pH? So again, I just want to emphasize that we're sort of in steps 1 through 4, and it'll probably take more of a community effort to get through steps 5 and 6. Okay, so now I'm going to explain a little bit about how we've thought about our case study application in the Northern Gulf. As many of you are aware, there's a summer hypoxic area that occurs annually in the Northern Gulf off of the Louisiana shelf. And it's driven by nutrient loads from the Mississippi River and lower Mississippi and the Atchafalaya rivers. And so on the right here is a time series of river nutrient flux from the mid-1950s through the mid-2000s. So this is the period of record that we have, and just looking at this record, we can see that there's been somewhere between 2- and 3-fold increase in nutrients over that period. So more recent work suggests that if we look at like the pre-European river nitrate flux, that potentially we're 15 to 20-fold greater than historic loads. So there's really been a big increase in nutrient loads to the Northern Gulf. And also the USGS had a report that came out a few years ago that showed that during the 2000s we were still increasing nutrient loads over that time period. So we're still kind of moving in the wrong direction from where we want to be going. And why this is important, let's see if I can get the slides hung up here. Okay, here we go. Again, we want to be able to model. People are now beginning to look at different nutrient sources in the watershed and figuring out different ways to reduce those nutrient loads, and every time there's a reduction, they want to know, well, what does it mean for Gulf hypoxia? So as I showed earlier, we're working on that kind of big multimedia modeling framework to handle that part of it. But more specifically for the coastal ocean, there's a hypoxic area goal that the Hypoxia Task Force has set up. And so in the lower right figure here, this is the time series of the midsummer hypoxic area that's measured by Nancy Rabelais et al. And the Hypoxia Task Force set a goal to reduce the hypoxic area to 5,000 square kilometers. And so much of our modeling is driven by, can we use the model to predict the load reductions required to achieve that management goal? And as you can see, for the last couple of decades, we've been hovering up here around 15,000 square kilometers. So, there's probably some pretty significant nutrient reductions that'll be needed to achieve the goal. Okay, so the actual application then is to this red area in the figure on the left. This is our model grid that covers the Louisiana shelf and the area where hypoxia occurs. And as I mentioned, the biogeochemical model has to be driven by a physical model. And so we use the Navy coastal ocean model, which is a three-dimensional hydrodynamic model, as to generate the physics that we then use for the CGEM model. So some quick facts about the NCOM model. We're modeling at a resolution, the horizontal resolution is about 2 kilometers. And then we have up to 35 vertical layers through the water column. We use the bathymetry is specified in the model, so just for any of you who are not keenly familiar with the Louisiana shelf, it is a broad, shallow shelf out here to about 100 meters or so, and the hypoxia is occurring in here, and I'll show you that. I think I may have taken that figure out, but anyway, hypoxia is mainly occurring between about 5 and 40 meters on the shelf. There are 95 rivers that discharge into the model domain, and they also, in the CGEM model, those rivers also carry nutrients and organic matter and other state variables. In the physical model, we also assimilate satellite sea surface height and sea surface temperature. We're trying to get the physical model to, as realistically as possible, represent the observations out there so that we can sort of remove that as a source of error from the biogeochemical model. And then critical for this issue of how does the ocean acidification mix or contribute to coastal acidification, we need to do a good job of handling these big open ocean boundaries. And so we use a parent model of NCOM called the Intra-America Seas Nowcast Forecast System. And so this animation on the upper right in this slide now shows that parent model. And so this model includes not only the entire Gulf of Mexico, but out into the North Atlantic and the Caribbean basin. And you can see in this model, you can see the large region of freshwater influence where the Mississippi River delivers to the shelf. And you can also see the very dynamic nature of these open boundaries. And so again, it's critical if we're going to be teasing out land-based issues from ocean dynamics that we have some way to quantitatively put these boundaries on here. And so we've been very pleased with using this larger, higher resolution model to drive our boundaries. And as a result, we do a very good job of predicting the physics. Some other aspects of the model forcing, clearly we're delivering the Mississippi River nutrient loads into the model domain. We also use for atmospheric deposition of nutrients and pH, we use the CMAQ model. This is an EPA air quality model. The community model for air quality, I think, is what that stands for. And also for the rivers, we use the relationships described in one of Wei Jiankai's papers, where he developed relationships between discharge, DIC, and alkalinity. So we're forcing the model with river inputs of those. And then on the open boundary, we also use the same DIC and alkalinity from that same paper. Wei Jian published a nice relationship between salinity and the CO2 system state variables that we can use to drive the shelf models. Now this figure is our high resolution shelf model, an animation of salinity also, and again, so now you can see the coastal currents, the region of freshwater influence from the river, and again, the very highly dynamic nature of this and most other shelf systems. Again, really pointing to the need to nest these nearshore models in larger parent models. So we've collected an extensive data set that we've used to quantify many of the biogeochemical processes that contribute to CO2 and oxygen system dynamics. And we use those data then to also help us quantify model error and model skill. We've had a data report that we published last year, Merle et al., that summarizes all the data that we've collected, and we're happy to share that if anybody's interested. Today I'll be mainly focusing on a couple of stations here that are highlighted by the red stars. One is station C6, which if you've done any work on hypoxia in the Northern Gulf, you're familiar with the time series and other data from this location. And then over here on the western shelf, this station is also located in an area where hypoxia frequently occurs. So in terms of model skill and error statistics for physics, this table here just simply shows overall compared to all of the observations, how is the model doing in reproducing temperature, salinity, and density, or sigma t. So we can see that in terms of bias, that we're actually doing pretty well. There's very small bias for temperature, salinity, and density. For root mean squared error, also pretty good errors. And then this model skill term, a model skill of 1 would indicate that the model reproduces the observations perfectly. So I feel like we're doing pretty good for all of these. And then just to sort of show you in a point-to-point matchup of model versus observation, this is a profile of temperature, salinity, and density from that C6 station, just from one point in time. And you'll notice that there's some disagreement between the model and observations, but please also note that the scales up here are pretty small, so these differences are pretty small overall. And then in terms of reproducing stratification, the density gradient is really what determines that stratification to a large extent, and so we're doing fairly well in reproducing that stratification as well. Now in the next couple of figures I'm going to show some time series of model versus observations, and I'm going to be focusing on surface layer, mid layer, and bottom layer, and so these blue lines just sort of show where we're going in the next couple of slides. So in terms of model pH, we're actually doing all right. In 4 of the 6 panels, the observations range across what our model is predicting, and I should note that these are stations where we sat on anchor for 36 to 48 hours, and so this is the variability that we observed at that east and west station over a 1.5 to 2 day period. The model is not reproducing that variability in these figures because we only output the model once a day, so it's not going to show the large diel variability in these graphics. I would point out that over here on the east station, we are under-predicting the observed pH both in the surface and the mid-water column. This probably points to the fact that we are likely under-predicting primary production at that location. The more primary production you have, the more basic it becomes. So this is an example of an area where we'll do some more work to see if we can improve that fit there. But overall, in terms of, especially in the bottom layer, you can see that the model is, kind of in general terms, reproducing the overall temporal pattern from, winter to spring to summer in pH. And similar for oxygen data, again, we're reproducing kind of the overall patterns. And I forgot to point out on the previous slide, the red and the black lines are different model structures. So this is sort of some of the diagnostic work that we do where we run the model with one configuration and then the model with another configuration, and we look at differences, and we try to figure out which of the combinations of those different structures give us the best predictions. So again, we're doing fairly well reproducing the seasonal transition from normoxia to hypoxia in the bottom layer, although we are missing some events like here on the east station. Okay, so how then do we take, once we, I'm not saying that we're there yet, but sometime in the next year or two, we'll actually be running model scenarios that we'll take to the Hypoxia Task Force and to other folks in the EPA to show, what the model is suggesting what nutrient load reductions are required. And so since we're not there yet, this is a sort of a conceptual figure that Dubravko-Justic put together going on almost a decade ago now, showing the kind of thing that we would like to get out of the model. So there's one aspect of the model that's critical is the uncertainty. So there's structural uncertainty, there's potentially multiple model run uncertainty, parameter uncertainty. In any case, we want to be able to communicate some kind of a cone of uncertainty around the model forecast. So if we were to example, the percent load reductions in this conceptual figure are down here on the bottom. If we were to look at the load reductions required to achieve that 5,000 square kilometer goal, this figure would suggest that somewhere between, maybe 50% and 35%, that's sort of the uncertainty around what's required to get there. And then we can also clearly, of course, look at improvements in oxygen concentration or improvements in pH, again with some uncertainty. So this is what we are, striving for with our nutrient load reduction runs, which will begin, like I said, later this year and next year. And so because the physics, I think, is probably the strongest part of our model, we have gone ahead and done some climate scenario impacts. So we looked at the recent IPCC report that reported on expected regional changes, and for the northern Gulf of Mexico, it's been suggested that anywhere between a 2 to 4 degree air temperature change by the late 21st century is likely. And we also wanted to look at how climate change might affect river discharge. So the IPCC is actually pretty silent on regional changes in river discharge, but there are some reports in the literature. For example, Sperner-Weiland suggested globally that there might be about an 11% increase in river discharge. And again, this is important because that freshwater contributes to stratification on the shelf, and obviously also for nutrients, there's an increased river discharge results in increased nutrient loads. And so how does all this, basically what I just said, summarized how this affects hypoxia, but increased temperature, decreased salinity, we should see an increase in stratification. We should also see an increase in primary production and respiration due to the nutrient enhancement effect, and then in some, those two things should lead to increased hypoxia. And there has been some simpler modeling done in the past that have demonstrated this. But we wanted to look at this in a 3D simulation. So again, we use our base year of 2006, and we did a climate run where we increased the air temperature by 3 degrees Celsius and increased the river discharge by 10%. The only other study that we're aware of that's really done this in a similar type 3D model is from the Baltic Sea, and they used similar types of increases, although a little bit greater, based on what they expect in the Baltic region, where they expect a little bit greater increase in temperature and greater increase in discharge. So with that future scenario, we can look at how that affects the physics of the system. So with a warmer air temperature of 3 degrees and 10% increase in discharge, it results in a temperature increase of about a degree for the Louisiana shelf and a small decrease in salinity. So these don't seem too striking. And they're smaller than what was found in the Baltic, but again, the Baltic, in that paper, they did more of a change. However, if we look at the vertical stratification, what this scenario says about that, this is the base year, the present year of 2006, and here we're looking at a side view of the shelf, and so the river would be coming in over on this part of the model domain, and then out here is our open ocean boundary condition. These red areas here are areas of high stratification, and then underneath that is where the low pH and low oxygen occurs. And so if we look over here at our future case, it's fairly subtle, but we do see that the stratification is increased, and the extent of that stratification is also enhanced in that future scenario. So what does that mean in terms of hypoxia? This figure then shows where the hypoxia is occurring in the model, in the reference year, and then in the future scenario. And so if we focus on this shelf area here, we can see that the blue areas here and here are about the same size. There's not a big difference in that area. But what is different is that in the future, because of that stronger stratification strength, we see more days in the model where hypoxia occurs. So here, the model is suggesting that hypoxia is occurring between 10 and maybe 30 days out of the year, whereas in this future scenario, it's occurring more frequently, up to 70 or 80 days. And so this sort of gets at something that we can't currently do with observations because we only have one midsummer shelf survey. We're not able to really characterize the exposure that the organisms out there experience, and with the models we can get at that. And clearly there's a greater exposure to hypoxia, and we haven't done this, or worked this up for pH yet, but I would expect that it would show the same thing for pH as well. Okay, so sort of summarize where we are and where we're going. We're currently working on different experiments, changing things in the model, isolating physics and biogeochemistry to understand how that translates to different model results. One of the areas where we're working very much on right now is this sediment representation, that sediment diagenesis. We need to be able to calculate the specific for acidification. We need to be able to quantify the internal versus external sources, and so the sediments are a key internal source and sink of DIC alkalinity and pH, so we're working hard on that. We're also using some optimization routines. This is a pretty complex modeling system, and so we want to be able to look at model uncertainty due to different parameters and different combinations of parameter sets. And we're also working in a model intercomparison effort, the coastal ocean modeling testbed, and I have one final slide that I'll show a bit of that, what we're focusing on there. And then these scenarios that are really the key for policy and management. Again, we want to be able to quantify any changes in land, air, and water loading, and how does that manifest in changes in Mississippi River loading and ultimately in Gulf hypoxia. And as I pointed out, we're interested in looking at climate change scenarios, and so the simple scenario I just showed you was sort of a clumsy attempt, just adding 3 degrees, adding 10% river discharge. But with the new generation of global circulation models that we now have at our disposal with these different scenarios for future CO2, we can more realistically model that and look at other things like, are there changes in coastal wind, direction, or magnitude? This shelf system is a very wind-driven system, and the circulation is driven by the winds. So any change in wind, would also have a big impact. And then something that we're just beginning now is another set of field and laboratory studies. Something that the Kai et al. Paper sort of laid out for the Northern Gulf, for the Louisiana Shelf, where low pH and low oxygen occur, but we don't really have a good way to take that and to say, for example, like in Mobile Bay or in Narragansett Bay in New England or in Puget Sound in the Pacific Northwest, where do we expect to see that combination of low pH and low oxygen, and then ultimately how much of that is driven by local versus open ocean processes. So I mentioned this coastal ocean and modeling testbed, and I think this is important. We're involved in this effort. NOAA calls this their only wet side testbed. So they have a number of different testbeds where they look at atmospheric modeling for weather and climate forecasting. This is their only ocean testbed, and within this testbed, the goal is to look at shelf hypoxia and also estuarine hypoxia and storm surges. And so as part of the shelf hypoxia team, we're looking at all of the various models that have been developed, ROMS, FVCOM, NCOM, and then different applications of those, and trying to isolate and understand why the models get things right, why sometimes they get things right for the wrong answer, and then where they really get things wrong. And again, this is sort of that extracting causality from observation and modeling. We need to understand and improve the models for both forecasting and scenario analysis. If you're interested in this, here's the link that you can find out more information. And I should mention also that the PI for this work is Katja Fennell at Dalhousie. And this has been a really interesting and enlightening project. Finally, in terms of the model that I've talked about today, we are trying, almost at a point now where we're putting together a website to make the code available. We have what we call the fish tank version of GEM. It's sort of a zero-order abstraction on the three-dimensional model. It contains the minimal set of boundary conditions and other inputs that are needed to run the code, and it can be run as a single cell, or if you have your own user-defined grid, you could link it up to it. But it's the sort of model that can be used for desktop modeling studies, or just for anybody that's interested in learning more about this model and sort of playing with the model to gain a little bit of intuition about how the model behaves. And this is something that we hear from our partners in EPA and other federal agencies, that they would like to not only get the model results from the modeler, but they'd also like to be able to play with the models themselves. There's always questions that the modelers don't address. Often the decision makers are only seeing what the modelers wanted to present. So this is a kind of an issue with modeling and transparency, and developing these kinds of tools is important for allowing end users to more evaluate the models and adopt the codes if they'd like. So with that, here's my contact information. Be happy to talk with anybody who's interested in this. And this is the shot of our facility. We're located here in the northern Gulf of Mexico in the Florida Panhandle. And hopefully I didn't use up too much of the time, and happy to take any questions if there are any. Thank you.
John, thank you very much for that excellent presentation. So we will open the floor for questions now. Are there any questions for John regarding his presentation? John, I have one. Do you have any information on how many people are using the fish tank gem right now, using that particular model?
I can probably count it on two hands. Not a lot, because we haven't got the first. We have a paper that's in prep that hopefully over Christmas break I'll get that submitted. But we are working. The Hypoxia Task Force is aware of this work, and we are going to get it up on a website shortly. And there are many advantages that I didn't have a chance to go into here for using the CGEM model. If you're familiar with modeling, kind of EPA's current model that's often used is WASP. That stands for the Water Analysis Simulation Program. And WASP has been updated frequently through the years, but it's still based on, I would call, first-order engineering principles, whereas in CGEM we've tried to keep the model up to date with what people in the field have learned about how these processes, the complexities in these processes, and so I feel like it's more realistic than the WASP model. But if anybody's interested, please let me know, and we're getting ready to make this available and to support folks that like to use it.
Okay, great. I have another question for you, and we've just got a little bit of time, so actually there's a couple of questions. What is the advantage of the MOSCI 2.0 model compared with the CO2 SIS, I guess SYS, in calculating the carbon parameters?
They're actually very similar. The MOXIE code has some more recent reanalysis included. So for example, like borate is a component of the alkalinity, and I think in the CO2 SIS there's a paper that relates borate to salinity, a regression relationship, and MOXIE has some updates to those regression relationships. So that's one aspect of it. I'm trying to think what else is important, but really it's mainly just about some of those newer reanalyses that have been done for really the components of alkalinity that have been updated in MOXIE to reflect some of the newer publications on those.
Okay, great. Thank you. That question came from Liking Yang, and Beth Gilliland asked, she says you mentioned Narragansett Bay and Puget Bay when you discussed the next steps, and she wants to know if there are any plans to apply this to Chesapeake Bay, which is, of course, another hypoxic area with high nutrient loads.
Right. We are sort of staying out of Chesapeake Bay on purpose because there's already so many folks working there, and also because EPA already has an established modeling system that they've used in the TMDL development for nutrients in that system. So we're trying to work in, there's a current need for this kind of modeling, and we don't really want to muddy the waters with yet another EPA model in Chesapeake Bay. So there's both scientific reasons and policy reasons for why we're not working there.
Okay, all right, thank you, and then we'll stop at the questions. Are there any other measurements, parameters in specific areas of the coast that would help inform the modeling efforts?
Sure. I mean, the weakest part of these models is really in the phytoplankton and zooplankton descriptions. For phytoplankton, I say this is a relatively complex model because we're representing 6 phytoplankton functional types, but there's literally thousands of phytoplankton species that occur, and so understanding what drives their community dynamics, interspecific competition between species, nutrient uptake kinetics, light kinetics, all of those kinds of things, occurrence of rare species, persistence of those species, and then the other part is on the grazing, the herbivory side. There is some knowledge about grazing microzooplankton, macrozooplankton, but very few studies that actually quantify those rates, and those are the rates that we use to parameterize the model. So I would say that those are a couple of aspects that we're going to be thinking about and doing some work ourselves and I would encourage the community to also contribute there.
Okay, great, thank you. So again, John, thank you for that excellent presentation. If we didn't get to your questions about the content today, please feel free to contact John via the email, which you can find in the right-hand side of your control panel in the chat box. And if you're interested in joining the SOCAN listserv to learn about future updates in the Ocean Acidification Network, please sign up at the URL shown on this slide, and please direct any questions about SOCAN to socan@sicora.org. We'd like to thank you all for attending these webinars, and this one in particular today. We welcome any feedback regarding this webinar series, and you can submit input by replying to the follow-up email that you'll be receiving from us shortly. And as I mentioned earlier, a recording of this webinar and a PDF of the presentation will be available on the SOCAN website. Our next state-of-the-art information about the presentation and how to register will be available on the SOCAN website shown here. We hope that you all will join us. John, thanks again for a very informative presentation, and thanks to all of you for your thoughtful questions and taking the time to join us today. We hope to see you at SOCAN's next State of the Science conversation. This ends the webinar.